All right. Hi, everybody, and welcome to the Ken Seminar series of Fall 2025. I am Johan Cárdenas. I'm a graduate student here at the Illinois Center for Transportation, and I will be serving as student coordinator alongside my colleague, Miriam Hafiz. We're very excited to launch this seminar. And to begin today's program, it is my pleasure to invite ICT Director, Professor Imad Al-Kadi, to share his opening remarks and introduce the first speaker of the Fall 2025 lineup. Okay, thank you. Could you introduce your partner too, Mariam? All right.
Good afternoon, everyone. This Ken seminar, we have been doing this for almost now close to 20 years. And the idea behind it is two things. First, to allow you to meet professors and academics and practitioners from different parts of the world, as well as within the United States, and to learn about technologies and science from others. But this could not be happened without the support that we got from the Ken family. He was one of the graduates of the University of Illinois. He was a contractor, he worked here, and then he has some funds that he allocated for the civil engineering. And he's the one who established the civil engineering alumni, which is the largest alumni of civil engineers in the world almost. So with that, his contribution to the civil engineering, which was as a gift, allow us to fund students, but most important thing is to allow us to have this Ken seminar that he is funding, and we have it every week. We decided to have a theme for the Ken seminar every semester, and this particular semester, we're going to be inviting speakers from across the country, as well as from Europe and other countries. And thanks to Miriam and Johan for arranging all the speakers that they are outstanding. They will be talking about the electrifications from the practical point of view, from the development point of view, from the recent technology in that field. So I'm sure, because I know who are the speakers, you're going to be enjoying this semester really well. So with that, the best way to start and kick off the Ken seminar, I'm going to go here. So this is some of the things that we did before, where we have even Kent around the world, where we have speakers from all over the world. But you will have the agenda for the different speakers that we have. You can register for this class as 0 credit. If you have not taken this class before, then you will take this class for 1 credit. And you will be asked to write a report about one of the seminars that you are attended by the end of the semester. That being said, it's always important how you can kick any program. And frankly, we cannot find a better person to kick off this program than Professor Ouyang. So I can talk for the rest of this seminar about him, but I can sometimes summarize it in a very, very simple way. It's not that he's just a very, very close friend of mine, but he is, of course, in my opinion, the opinion of many of the scholars, that he is the best optimizer that we can have in this country. So to have the program kicked by Professor Ouyang is a special thing for us. He's also the associate director for the ICT, and he's a named professor within the civil engineering department. And above all, he's the nicest professor that you can have. So that, oh, there it is, Professor Ouyang. Please,
This is working. Well, good afternoon, and thank you, Dr. Cardi, for the very generous introduction, and then thank you all for being here. It's a great pleasure to come back and then give a little bit presentation about some of the work I and my colleagues, including Dr. Cardi, actually, who have been working on for almost a year and 8 months. And then this is about developing a computational and data platform for freight mobility. And I know that the theme of this semester is electrification in mobility. We will talk about that, but we'll also go a little bit beyond that. In a sense, we are trying to provide a platform for not only electrification, but also other decision-making, including mobility, including infrastructure investment, and so on and so forth. So we will get into that. But with that, I would like to really acknowledge the contribution of a lot of people. I have the fortune to work with a big team, including many of us from the UC team here, and also from the UC Irvine, and also from Oregon National Laboratories. I acknowledge the leadership of Dr. Richie and Dr. Lupita. They lead the respective teams. And then here, I want to mention that your friend Angeli is our tech to market lead. So she has contributed quite a bit. And also, I would like to also mention other Dr. Cardi is here, Moran is here. They are part of the team. And also, I want to mention Yanfeng Ouyang, who is not here in the audience, but he has been my right hand on a lot of the work that I myself do as part of the team. So anyway, I just want to acknowledge their contributions. Everybody, thank you very much. But I also like to mention briefly that ARPA-E was very generous in supporting this project, DOE ARPA-E, and then we had great advice and then suggestion, comments from the directors, Dr. Robert Ledoux, and also now Jeffrey Snyder, and also the team, Dr. Achaya, and also Dr. Agawa. So we also had industrial advisory board from some of the leading freight companies that really have experts that are giving us a lot of advice about how freight should be doing, so that we were benefiting from their input. So with all this, I would like to sort of kick off a little bit about why we are even doing this, right? Why I also want to compliment DOE ARPA-E for even initiating this program. They recognize, actually, I think this has been the situation for decades in this country and worldwide. The freight system compared to passenger system, transportation system, suffers some unique challenges. Essentially, for example, the data just give you one example, because the data in the freight system are very often proprietary. It's all business, secrets. Compared to the public side of passenger transportation, it's all public. So in a sense that to get data even to understand how the freight are being operated, it's a challenge. We actually ourselves also suffered that as well along there. So we were trying to develop, understand, sort of even have data that can really give us more coherent sort of a picture of how the freight is being operated. That's actually one of the motivations. But also other things I can just mention them briefly. We know about the freight systems is a big contributor to emissions and energy consumption. We don't need to say too much about that. And also freight systems have been suffering from sort of disasters and also disruptions. I'm going to show you a few examples that you have seen probably in the news in the recent years. Remember the Baltimore Bridge collapse and how the supply chain has been disrupted for various reasons. So anyways, all those things, and then we are trying to really address all these challenges, among others, to really have a platform to provide a sort of a one-stop hub where we can get data access, where we can get also computational support to the decision makers regarding how freight should be operated, at least. And then when some disaster happens, how the system can recover. We can help the system recover even faster and better. So those are the things that we were trying to address. Thank you. So one slide overview of all our efforts that we're planning to do. We have a few matas here. I like these several matas. We are really addressing the data that are coming from multiple sources that very often have different resolutions and different scope, temporal and spatial. We need to be able to try to compile all this data, fuse them into one coherent and integrated platform. We have multiple levels of decision making. We have different decision makers in the system. Shippers, carriers, government, and then other stakeholders, they have different objectives. They have different constraints. They interact with one another. We need to be able to address all their decision making along the way. We also need to have a platform that integrates all this different decision making and data into one coherent framework, right? And so we also have to actually address multiple objectives. We clearly in the freight industry, because it's private and so on, obviously cost is a huge factor that people care about, right? Profit, cost, dollars. But then also in addition to that, the freight industry actually also care about even more sometimes about the shipment time, the delay, and also the reliability. You order something, can you deliver that on time is a big issue because sometimes the delay leads to cascading effects down the supply chain. So they need to make sure that things are going to be on time, reliability, and also in recent years, more and more importance is put onto decarbonization because of the emissions and then the sort of a sustainability concerns. So we have multiple objectives as well. So what we have been doing in our project here, we have been, this is a little bit covered, but here is actually different scale, spatial scale. This is essentially from local regions to national level models. Essentially, we are covering different scale and different resolution over space. We are covering multiple systems. We include the multimodal transportation network for freight, including highway, railroad, and waterway. And then we are also considering the accompanying systems such as the energy system and also the accompanying natural disasters, the sort of the biophysics systems. Thank you. Then we also consider a simulation platform that we're trying to build. Thank you very much. To try to make sure that everything is going to be integrated together. Within this sort of a framework, what we do is that we try to first, we need to get the data together. Oops. We need to get the data ready. So our partner, UC Irvine, has been developing sensing capabilities on highways and also on railroads to detect in real time the container passing. And then we will have information about, on some of the part of the networks where the traffic is and what's going on. Then they have been doing a lot of data fusion, cleaning, and also the integration effort. But then that's not the only thing. We also integrate everything that we can get from public databases. We cannot, unfortunately, go to companies and ask for their proprietary data. We have to use public database in addition to the sensing that we have. We basically collect all the available. We tried our best to collect all the databases that are available in the country or in the world, I should say, for this country. And then we try to put them together into multimodal system. We integrate them into a sort of a data hub. Everything we try to put it together and then fuse them together. And then this is obviously Irvine and us are working together on that. Then having all this data enable us to make decisions. What type of decisions we make? Some of the decision would be, we try to understand how shippers and the carriers. Shippers would be those who are shipping things around, you deliver a parcel, you are one of the shippers, okay? And then the carriers are the people who actually do carry the parcels around, the goods. So shippers and carriers make decision about which mode they use. Should this 5 containers go through the railroad or go through the highway? That's a question. Or go through the waterway. And then if either way, either mode, how they are going to exactly route the traffic, how exactly that's going to happen. So these are the logistics decisions that we try to sort of understand. With that understanding, we try to then incorporate the external disasters that may actually affect the operations. If we try to understand the disruption risks, then formulate them into scenarios, and then understand how the logistics systems, freight logistics systems, is going to be subject, how they're going to be impacted by the disasters, and then how infrastructures should be fortified against those disasters, how we can recover better. Then we also try to understand, of course, if we have alternative fuel, zero emission options, then how they are going to have an impact, and what new infrastructure, such as electrification, where should we build charging stations such that we can best support freight movements in the country? All these things I want to mention, all these type of decisions that we have to make have to be based on understanding of the logistics operators, because we invest in the infrastructure, then the shippers and carriers are going to react to that. We need to understand their reaction before we make investment. I hope that makes sense to you. And then they understand their behavior. We need to have data to support our understanding. So that's sort of the logic coming down this route. Then we also work very closely with Argonne to develop simulation environment and test beds. And then this simulation environment and test beds not only serve as a final validation platform, but also they provide very important data for us to make decisions. Because sometimes this data is still not really sufficient. We do not have, again, the data is proprietary. We have to have some synthesized data in order to support our decision making. So we are really working in all fronts possible to try to resolve the challenges in the freight system. Okay, so with this is just a framework. Then this is a slide from Angelique. I copied from here. we are trying to provide a multimodal, multi-scale, and a multi-data source platform with data provision and decision support capabilities. Well, the decision support we try to provide, we give them the data, we help them figure out how shippers and carriers can use our system to understand how they should send their containers through the network. What is the best way to ship things? Then government and other agencies, maybe industry, consider where they should be investing in the infrastructure, such as energy infrastructure, including charging stations. Okay, so this is sort of the framework that we are trying to, or the scope that we're trying to cover. So a little bit about the data. I'll go rather quicker now. I hope now it's clear what we're trying to do. A little quicker about the data. I mentioned that we collect data from existing public databases. We do not rely on proprietary data sources. Right? So from highway, we got the FAF, Freight Analysis Framework, and we got the railroad database waybill datasets. We got the waterway datasets about their cargo shipments in waterways. Then we obtain also the FEMA database regarding the hazards. Remember, we need to understand a little bit disasters, right? So this is here. We also, because we are considering electrification, we also collect the data. We don't really have the real data about our electricity grids because that's the national security. We cannot get that. But then some colleagues provided some synthesized grid data, which we can use as a proxy for now. Okay, so we have that database as well. We put them all together, but also where our colleagues in Irvine has been developing sort of sensing capabilities. They put camera and the LiDAR sensors on the roadside, either railroad or highway, to really in real time track and identify the containers that are passing. So just maybe a little bit here. This is actually a video. I hope it's gonna show. Okay, it's a long video. I'm only gonna show like a few seconds. Essentially, they put on the roadside. This is a LiDAR, sort of a stream. Whenever a truck comes by, you will see some updates here regarding, I hope the truck comes by. I think one of this is gonna jump. Yes. Jumped, right? I didn't see actually. Okay, I'm too close to the book, but trust me, it's gonna jump. They actually in real time identify vehicle passing and the type of container you have, and a vehicle and the container passing. Anyway, you trust me? That's what they did actually. Oh, trust them, right? And then they also put this on the railroad side to track the trains. Then they have installed particularly testbed in California. This is also a little bit of I'll jump a little bit. It's gonna take long, but then they have this type of all the data from about 32 sensing sites. You basically have samples of the traffic in the network. They can integrate them together in real time updates. This data is now fed into our system at UAUC. So anyway, so this is a part of their effort. This data is in addition to the static data we got from the public databases. This is a real-time sensing data. So you see. Then also our colleagues at Argonne have been for decades have been developing Polaris. It's an agent-based, activity-based simulation platform. It gives you detailed sort of a traffic simulation in a certain geographical region. They have done particularly test cases in Chicago and also in Los Angeles, which fits our project very well. They have detailed, basically behavior-based type of a generation of traffic simulation. So this data could use as another supplement that we can use to try to supplement the gaps that we have in other databases. So we have been using all these things together. Again, just to show how we integrate things together, we have real-time data collection. We have the Argonne sort of activity-based, agent-based simulation data. Then we also have the static databases from public sources. We put them together into a multimodal network so that we have information about the entire network, about traffic flowing. And then we particularly have Los Angeles and also Chicago in a higher resolution. The rest of the country, we don't have as much resolution, but we really build a multi-resolution database and also the network here for us to do modeling. With this setup, data integrated together, we're now able to make decisions. So decisions including, for example, lifecycle assessments, which Moran has been working on with Dr. Cardi, and also, for example, disaster impact assessment and recovery decision making, which I'm going to talk about a little bit next. So next about decision making. So I have here, I'm going to talk about this is part of the work I have been more interested in working on. So we are more or less trying to do this large scale sort of logistics decision making. In order to better improve the freight system, we first need to understand how it's even run, who are making the decisions and how they make decisions. We need to understand how shippers and the carriers really route their traffic in the network. First understand that, then you can go in and try to make changes to it. Does that make sense? I hope, right? So one of the first challenges that we have to address is that we are dealing with a very large scale network, and then the whole continental US network, all the highways, railway, and also the waterways. So we make in order to model this network, we make a few assumptions. We assume that, again, some certain levels of rationality. This is common in the transportation system side, where we assume people do the best for themselves. Every shipper, when they ship, look for a certain best option they have. Rational humans, right? Okay. Then we assume that actually the system, it tends to be stable. If there were any disturbances to it, such as disasters and anything, the system tends to evolve back into another equilibrium. The equilibrium exists, and then the system tends to evolve back to the equilibrium. This is a sort of a hypothesis we make, but reasonable, I think. System tends to stabilize by itself unless another shock shows up. Okay. And then, but we also have a third one, which is sort of a relatively interesting, is that we do allow certain regional networks to be not rational. What I'm trying to say is that actually we allow heterogeneity in the network, meaning that we also allow certain irrationality in the decision making. So we think that certain local neighborhoods, due to lack of data, we may not really understand that network fully well, which is, I hope, reasonable. As much data we can collect, you probably don't know every corner of the country, right? Then we want to allow such imperfection in the data, but still be able to learn what's going on. So we basically build a hierarchical network where we assume a shipment happening across the country in the large scale, at a country scale or nation scale. It should be sort of looks like rational. I'm going from Los Angeles to Chicago. I'm gonna head northeast. I'm not gonna go the other way direction. You know what I'm saying? On a large scale, I may be in the right direction, rational decision. But I'm not gonna go a straight line. I may actually detour around a certain neighborhood because of certain reasons. Does that make sense to you? There may be some local heterogeneity or unknown that prevents a straightforward route choice. So we allow that decision. We allow certain local subnetworks to be displaying heterogeneities in it. And then the problems, the decisions or questions we are trying to answer include that what type of shipment for the shippers and carriers, how do you route your containers through the network? And then for the government and the industry, how do you invest in the infrastructure? Sort of decisions we make. I want to expand a little, maybe this part is expand a little bit the idea I just mentioned. We try to, instead of dealing with the entire network that we see on the top there, which has millions of links and nodes, millions, literally. And then we try to basically imagine that we can sort of abstract that network into a simpler one. How do we do that? We imagine we have some backbones in the network. For highway mode, we have some interstates serve as a backbone. Right? You have a really like a spider web, but then we pick some of the backbones, and then we assume all the other local roads are like a sort of like a patch that are attached to that backbone on top of it, which provides alternative routes if people need to detour from the interstate. Right? We have capacity for people to get away from the interstate and come back, but then we have the interstate backbone, and we have the local routes as the backups. Okay, locally. So we have and then the local ones, we allow information to be imperfect. We do not have to know every little detail of that local network region, but then we are gonna try to learn about its properties. When people go through Champaign County local roads, what their experience is, we don't have data for that. But we observe how many people choose to go through the locals, suppose, of Champaign County local roads, rather than I-57, I-74. By having that observation, we may be able to come back and then infer some information about the local roads in Champaign County. Is that okay, something? We sort of, rather than care about the details of Champaign County, we try to learn something on top of it so we use the neural networks to try to learn the regional network property. Okay. Then we put them together, and then we do the overall modeling. And then this part allows some local behavior. So locals knows the decision makers, shippers, carriers may choose to avoid certain regions and go certain regions. Like we don't need to know everything about it, but by observing people making those choices, we can infer certain things about those regions. That's essentially the idea. I hope that makes sense, roughly. So anyway, so that's the idea. This is an example of it. I'm not going to go into the math here, but the idea is again, for example, this is Chicago, right? Chicago, we have the interstates, which we use as a backbone example. Then whatever happens in the downtown area, we gave up on tracking the details of the local downtown area, but rather we use a so-called hyper edge to just imagine it's like one link in the network now that allows multiple entry and exit points. It's like a one super corridor there. You allow people to travel through it. We want to know, basically, we use a neural network to try to estimate some properties of this hyper edge. For example, one property would be if people are coming in and out of this area, how much congestion happens inside. You give me an arbitrary distribution of traffic from entrance to exit. You give me an arbitrary profile of traffic entering and exiting. I should be able to I want to predict a congestion pattern inside. That's all what we are trying to do. So we, instead of dealing with all the little details in the downtown Chicago area, we deal with one hyper edge. You can see that's how we reduce the size of the network. So hopefully with high fidelity. So anyway, so with this approach, I'm gonna, oopsie. With this idea, we use a neural network for each hyper edge, and we use a neural networks to learn how the flow through traffic versus the congestion pattern inside, basically. We have a quick way of learning it. And then this hyper edge neural network will be trained by whatever data we have. I mentioned about different sources of data from Irvine, from Argonne, from databases. We use them, we can train offline. Whatever data we can have, we dump them in there and learn the neural network. Then we can use that hyper edge representation surrogate back into the global network model without all the details. But we have a good representation of the locals, right? I hope that makes sense. So just really quickly, we did this for the nation. This is actually the backbone of our system right now. We have the US networks. We partition them into, I'm actually colorblind, so I don't know which partition. Ido did this, and I have to confess, it's a mess to me, like a mess. So I cannot see the colors very well. But this, maybe you see better than I do. So it's a different partitions. Each partition is a hyper edge. Okay, how about that? Anyway, so we were able to show that the error can be. We basically in this it's a validation we tried. We have to assume a ground truth. We don't have the ground truth right now. I have to confess, we don't have ground truth. Nobody right now knows exactly in the United States how freight is moving to the accurate value. It's all proprietary. It's all fragmented in different databases and so on. But then for us to validate our model, we can assume a traffic pattern as ground truth. Then we try to see if we can reproduce that through our model. We were able to achieve some sort of reasonable errors at a national level. And then we are by having this type of a hierarchical hyper edge type of representation, we're able to speed up the computation quite significantly, even for this network. We're happy with what we have here. This suffices for the need. And then with that model, we actually Moran and Dr. Cardi's work here is showing that we actually now have the traffic flow modeled. We then translate that into life cycle analysis and try to understand the emissions and everything. So this is a part of. I'm just gonna have one slide to summarize that. There's a lot of work that's ongoing right now to understand the emission impacts and so on. Okay. So by now we have a network calculator, maybe, or like a toy to play with. Now let's play with it, right? You have a new toy, ChatGPT come up, you just ask random questions to it, right? Just for fun. That's what we did. When we have that tool ready, we are now able to model the traffic in the entire country. We can just play with it. So some of the like the questions you put into ChatGPT would be like, say, what if, right? What if I'm gonna try to divert the traffic, free traffic from highway to a more sustainable mode, let's say rail and others, what will happen? So this is the example of showing the impact on emissions. Okay, I cannot go into the details, but just trying to tell you that we can just play however we like. We can play, let's say, let's all the emissions on the highway network, suppose 50% or whatever percent gets diverted into other modes. Let's evaluate the emissions. We will be able to come up with a certain basically this will be useful for policy decision making, right? Essentially, how much we want to divert the traffic, how much incentives we give to different modes, something like that. I'll go rather quick. We can play however we like. We can play what if disaster comes or whatever. Maybe I-95. I cannot think of a reason. Just for some reason I-95 gets shut down. I-95 is a corridor from here to here. It's probably considered to be one of the most congested free corridor in the country. What if that corridor gets somehow discontinued? Okay, for whatever reason, and then what will happen? We will be able to actually allow such scenarios to be analyzed. Just like you have a calculator, you just enter some numbers and play with it. And then this is some results we show. We will see basically the observations actually, if we have I-95 corridor from DC to Miami, the entire capacity, no disruption, 50% capacity loss, 100% capacity. We can do whatever we want. Then we will be able to tell how traffic gets redistributed. It turned out that actually some of the traffic, as you can see here, basically traffic gets diverted into some other neighboring roads, and particularly local roads we found serves a very important role. So basically, if a certain corridor gets disrupted, then the trucks tend to go to some arterials nearby. That's a backup road. That's what we found too. So anyway, we will be able to have quantitative sort of a prediction about what's going to happen in the country. We will be able to play with this and say, what if I-95 capacity gets lost different percentages? How is that the impact to the nation? So this is about the traffic shipment diversion into some other roads. We would have such summaries about it. We have actually the detailed pattern, but we could have some statistics to summarize what's the impact. So there are some certain this could be some policy implications about how important I-95 is. So anyway, I will not go into the details here, but then just to show you, we played with this. This is really fun. Another scenario we worked on is what if Los Angeles area somehow for whatever reason all the ports closes for a certain amount of time, then our model was able to predict that there will be a lot of traffic diversion. The international maritime shipments has to go elsewhere through the rest of the nation, other ports. So these are some of the alternative ports. Basically, every shipper carrier, you make the rational decision about they need to ship to Chicago. Los Angeles is not disrupted. Then where to go? They can go to Seattle, they can go to elsewhere, they can go to a different place. Actually, Seattle is not here. Shame on me. I thought Seattle should be one. But then they go to Baltimore, they go to the East Coast and so on. This is our model prediction that what's going to happen. Okay. And then we were also able to show how the essentially also then this entire reroute of the traffic from avoiding Los Angeles area. Now, how much is the impact on the national network? Different parts of the nation. Okay, I'm going really fast on this. This one I thought I should show you. I thought it was fun. This was in the news, right? Like 2 years. I forgot which year. 2 years ago, the Baltimore Bridge collapsed by a vessel. The collision that we had. It's in the news. A huge, high-profile situation. We played with it a little. Let's see, just for fun. You have a toy. Let's just play with it, right? We play with it. The idea is actually there's a bridge that's collapsed. By the vessel, and then so there are two impacts, immediate impacts. One is that obviously that bridge can no longer be used. That's one. So the highway network gets disrupted. Second, because of the collapse, actually it blocks the waterway to the Baltimore port. That's actually the big one. That's a big one because the Baltimore port gets effectively disabled. No traffic can go through the waterway to reach the Baltimore port. So we modeled that, and then we were able to show. Essentially, we were playing with it and to show under different level of capacity loss, how much is going to be the impact on the nation in terms of the truck traffic rerouting going around. Or the port traffic, actually, I want to show you this one. The why Baltimore local bridge collapse, one bridge. It has been said in the news that the whole nation felt it. The whole nation felt it because the traffic gets rerouted to all the traffic that was supposed to go to Baltimore now all over the place elsewhere, right? So anyway, so these are just to show you that how this tool can be played. It's very I find it fun. Okay. Last part, I will go really quick. I think I have a few minutes. About the last part about investment. This is because this project is still ongoing. It ends next summer. We have about a year now. But then this part is the last part of our project we are still working on regarding. Now we sort of understand how traffic is going to be flowing through the network. Now let's look at the network and decide what we should do to the network, such as to make it better. That's the question we address here. Either we have to improve the network capacity for the transportation network, or we can improve the energy infrastructure that make the system more sustainable, right? Charging stations, for example. So actually, Ido and I worked out a little. Ido mostly actually he's the mastermind developing this, working on this. Is that we develop a so-called freight charging station location model. The idea is actually quite simple, but it's interesting. The basic idea is the following. Well, maybe come back to this. We have this network in front of us. We have some budget, let's imagine, to electrify some parts of the network. We can build a certain number of charging stations in the network. How about that? But the question is that where do we build it? Then we have a complex network with all the traffic flowing around. Every traffic has an origin destination, right? Passing through some, we know we have a prediction now about how the traffic is going to go through a certain path. But then the question is, where do we put those charging stations to serve the most we can? So, and also another thing I wanted to mention is that really we need to understand that a certain installation of a charging station would serve a certain trip from origin to that destination if that charging station is somehow on the corridor of its path, right? Sort of, unless you allow the truck to detour around. And also, secondly, is that to say the installation of a charging station may serve multiple OD passes that are passes through a corridor. Okay. And anyway, so essentially, essentially the problem here is the following: we have now a network of transportation. Let's say highway network for now, charging stations, highway network. Then we basically consider a certain truck trip to be covered if we install stations along the way such that the truck can recharge along the way such that it never runs out of battery. How about that? We consider that trip covered. So we try to find the best location such as to cover as much as we can. And also, we need to understand that sometimes a trip requires multiple charges along the way, in the middle, right? And then if you have a choice of putting two charging stations in the network, even along the corridor, you can put these two charging stations very far apart. You charge some vehicles here, charge some vehicles here. The benefit is not as big as if you put the charging station somewhat strategically nearby, such that a longer trip can be covered. Am I making sense to you even? For example, a truck can travel 200 miles per charge. If you put the charging station too far apart, you can only support some local trips here. But then if you put them somewhat strategically, you can cover a 400-mile trip in a bigger area. So there's certain combinatorial relationship between the impact of charging station if you put them in a strategic location. They help each other. They jointly serve some trips of a longer distance. I hope that makes sense to you. So anyway, if that's clear to you, I can skip all those things on the right. This is an example to show you a strategic location of charging stations could make a difference, even you give the same number of charging stations. Okay, so I'll skip this. This is all okay for the math. But the idea is that we have some models to do it. Trust me. And then we have some algorithms. We actually benefited from some literature. I did some work in the old days for the railroad network about sensors deployment in the network. But there's some similar ideas we can use. Some colleagues work on this as well. This algorithm based on algorithm relaxation. Those of you who are interested, we will be able to effectively solve this for the national network. So really quickly, if we were to electrify I-95, this is a scenario we play with. So you are basically given a certain number of, the government says, let's invest about, let's say, 100 charging stations on I-95. That's a budget we have. We can do this, right? The government, FHWA, was talking about every 50 miles per hour, every 50 miles or so, a fast charging station. We actually think, we may be more, we can do better potentially, in a sense, we need to strategically put them. into locations that we can save some cost. And then you understand what I'm trying to say? We can do it in a more optimal way. But anyway, so we actually will be able to electrify this. We know even along the corridor, we have trips starting from anywhere and ending anywhere. You have trips going from everywhere to everywhere. Then where do you strategically put the charging stations such as to serve as much as possible? We basically come up with the optimum this frontier, given the number of charging stations, government investment level, how much we are able to support the traffic and then reduce the emissions. We assume that actually if a certain trip can be supported by the charging station, that we have the opportunity to replace that truck by an e-truck. Then we compute the emission reduction, like something like that. So these are some of the examples. So if we have 5 charging stations to build, if I have 10, where they should be, they are not evenly 50 miles apart. No, we should not. Sorry, I shouldn't say we should not. We can do better. We can actually strategically co-locate or jointly put them in some neighborhoods to cover the most heavy traffic corridors. I hope that makes sense to you guys. Not evenly distributed everywhere. Okay. Now we played with the United States entire network. This is some solutions. We even compared to because there's no solution right now. We basically do some greedy heuristics. Like I said, we just basically, the simple solution without our model would be look at this network, look at every location that I can build a charging station. I compute for each installation how many trips I can cover. And I can just select the biggest, and I until I run out of my charging station numbers. That solution is this greedy solution. Okay, that's sort of the quick and dirty way of optimize. We can do way much better if you have a model. So I'm trying to tell you that this is meaningful. That building the model is meaningful. Okay, with this, oh, I think I'm running out of time. So 1 minute to. Dr. Calipo and his student Cheyenne prepared a quick video about the portal we are developing. This is actually our ultimate product from this project. That everything that we have been showing you will be part of this to give people a support for decision making, data visualization, data access, and everything. So this is a quick video of the portal. I'll skip the first few. You have seen this. This is going to be public when the project is over. We are going to be running this system for public service. These are the people that are involved. I'll skip this. I'm jumping. Sorry, jumping. This is our industrial advisory board, and then I'll jump. This is how this data visualization we are able to show. Sorry, I have to jump quickly. But those of you who are interested, let me know. I'll be happy to send the video over. This is still under development, but we're able to show different type of metrics that we care about, and then the network, like what type of data. This is visualization. Let me jump a little bit to the next. Data visualization is one part, but I want to do the decision support really quickly. So this is where we start to do decision support. We allow this video is very big, so it's thinking. I click multiple times. It's thinking. Okay. What did I do? Maybe I'm doing.
Should we quit?
No, no, it's fine. I think it's probably just it's not responding to me anymore. Clicking. Anyway, I think, oopsie, I jumped.
Okay.
I don't know where I am now. Should. Oh, this is stopped. Sorry. I don't know. I'm probably click somewhere. Anyway, okay, thank you. So maybe I cannot show you the whole thing, but the idea is actually we allow people to choose an arbitrary, imagine the United States here, choose an arbitrary region where any capacity disruption may happen. Then we will allow them, we will be able to consider how much capacity is lost in it. Well, and then we will be able to tell them what the impact is. And then how under touch impact, how you should be sending your containers, route optimization. And then we also tell them under the situation, how you should be recovering your network, where you should be building things. We have a further sort of a dialog box showing up next under there to allow them to make decisions. Essentially, all the three sets of decisions I mentioned earlier. Okay, how shippers carriers should be shipping their containers. Anyway, so it's a little bit too big, I think. Even the video is not working to me. Come on. Anyway, maybe I should not stick to it, but just to let you know that we have all these things implemented, and then Dr. Caliper has been really helping developing this portal for us to implement all the decision support we have. I think this is the end of it. I think that's the end of it. So thank you very much, and then I'll be happy to, if I have time for a couple of questions. I don't know. Thank you. Yes, please.
Thank you so much, Professor, for the nice presentation. I have a couple of connected questions, basically. The first question is, have you incorporated FHWA's existing plan of electrification, since they already have infrastructure, especially the east and west coast, they're almost EV corridor ready? And where does that come into your plan? Because you are coming up with a new suggestion, but they already have infrastructure on such locations. And the second question, which is connected to this, is that you've said that you'll be coming up with a recommendation of having renewable energy infrastructure. So do you plan to first looking into what the grid composition is? Like, suppose at some places it is fossil fuels based, and the others it is renewable based, and then coming up with a recommendation of prioritizing infrastructure based on the grids that's there.
Great question, first of all. Thank you. Very relevant. The first question about FHW current plan, we have not looked into that. The reason is that we are currently most focused on developing this decision support. And then we have not checked whether FHWA's current plan is optimal or maybe it could be further optimized. We think we probably could, we could do better potentially if we were to optimize, but we also recognize that there are other considerations rather than just our optimization have certain objectives and certain constraints that may or may not be the same as what FHW had. They develop their plan. So I'm cautious about just directly do a comparison. I only was trying to tell you that certain intuitive solution may not be suitable. Like evenly spread them out may not be the optimal solution to make every 50 miles. Maybe not. So hopefully that answers your question. Partially, we could play with it later once we are developing the calculator. There are a lot of things we can play with later, maybe. Okay, that's one quick answer. The second question regarding the alternative energies, we plan to work on the hydrogen supply infrastructure at some point. We haven't covered that. We are now still, as I mentioned, this type of investment decisions are the last part of the project, which we are in the middle of it. We haven't done work that we were considering potentially energy production, hydrogen production, storage, and sort of a charging or fueling capabilities. We haven't done that yet, but that was on the plan for the next few. We still have a year almost, so we're gonna work on it. Yeah. Thank you.
We have a question also.
Okay.
From Jesus, if you seek to maximize the number of trips covered, would that overload some charging stations? How do you consider capacity and delay while charging?
Excellent question. At this point, we haven't considered capacity, Jesus. This model is developed very recently. We are going to continue to implement that. That's a sharp observation. Jesus was my recent graduate. He's now a professor. So that's an excellent comment. Yeah.
Thank you, Professor. I actually had a question about one of the assumptions of the model. Maybe I'm just unclear about the definition of equilibrium, but I was just confused. If we assume that after a disaster, the system goes back to equilibrium, then how do we assess the impact of accident on the system if it's not to equilibrium?
Oh, the equilibrium could be a new equilibrium. It's a different equilibrium. Okay, it's a different equilibrium. Okay. The system can have different. So maybe you can, actually, it's a very complex problem. You give me a network and then you let traffic, everybody choose the best way to travel around it. It could be unique equilibrium, there could even be multiple equilibrium. Depending on. And then when you have a disruption to the network, there definitely likely will be a new equilibrium.
Okay.
Unless you repair the network.
Okay. Okay.
Is there any other question in the room? Go ahead, Lama. Yeah, perfect.
Thank you, Professor, for the presentation. I just have two quick questions. One is related to, I was really interested in how you patched all the local roads on the backbone. And I feel like most of the calculations you're doing are related to this neural network that you are predicting the
Yes.
congestion. So I was thinking, is that the only thing you're predicting, the congestion? And how to calculate everything else, the time delays, the cost, the emissions, is it just the congestion or are you calculating something else?
Excellent question. So the prediction of a congestion is actually by links. We essentially, okay, so I'll say this. Everything comes from the flow distribution inside the local network, right? Once you have the flow, I was trying to be avoid the details, so I didn't talk about the details. We are really predicting the cost from origin to destination along a certain path, actually. And then once we have the cost, we can quickly compute the flow on it. And then we will be able to predict anything like emission levels on top of that. So essentially, everything is related to the fundamental flow distribution on that. So we are trying to predict right now we're predicting the cost, but then it's the same thing to predict the emission and everything else based on that the same flow same network. So I hope I answered your question partially, but yeah.
That's great. And we will have one last question for today's session as we are almost on time. Professor Kuntu, would you like to unmute yourself and ask a question?
Yeah, definitely. Thank you, Professor Ouyang. That's great presentation and overview. I wondered if the decision making for charging takes into account cost associated with charging, which could be also affected by the grid capacity, and also this could affect the behavior of the tracking provider. Essentially, this could change the distribution of track departures and affect the OD matrix, which I guess delves into dynamics. So I'm not sure whether these kind of feedback loops are planned to be taken into account here.
Well, excellent question. Thank you, Ria. The short answer is that no, we didn't consider the temporal scheduling of things right now. This is a planning model, so we are really doing the high level planning just to get the coverage over there. We didn't do the operational level decision making yet. So basically, those are what you mentioned are all great ideas to further sort of enrich the model. This is a very recent attempt, so we definitely would consider that in that direction regarding scheduling of the detailed operations. Even you mentioned about the track scheduling, right? That's a great idea. We haven't considered that.
Thank you, appreciate it.
Well, Professor Ouyang is going to stick around for those that want to ask further questions, but for today, let's thank him for this insightful presentation.
Thank you very much.